Sure. Hello, everyone. Can you hear me?
Yes.
Okay. So my name is Khoder. I'm a PhD student at the Indian Institute of Technology, Mumbai. And I would like to thank you for attending my presentation on adding an explicit Godunov type solid model to solids for form toolbox. So, let's see. Yeah. So for the content of this presentation, I will start with some theory, and then I will talk about the structure of the explicit solid dynamic toolkit that I will be using for introducing a new solid model. And then I will talk a little bit about the structure of solids for form toolbox. After that, I will show the steps of implementing the explicit Godunov cell center, for short CC, solid model. And finally, I will present one test case for verification. So for the theory part, um, so what is fluid-solid interaction, FSI in short? It's the domain where we have the interaction between fluid and solid. It could be a surrounding fluid or internal fluid to the structure. And here in the slide, you can see the test case that basically I will be solving at the end of this presentation, where we see a flexible pile in cross flow. So why finite volume method for FSI? Basically, finite volume method has been a robust foundation for numerical simulating for fluid and solid systems. And the available software for FSI usually are partitioned. People are like combining different solvers, something FEM, something FPM, and creating some compilation, coupling algorithm between these different softwares. However, in my opinion, one of the best software available right now for fluid solid interaction, along with finite volume, is the Solids for Form toolbox, which is obviously built on OpenFOAM. So the goal of this project is to extend the Solids for Form toolbox with a novel solid model. The novel solid model is based on momentum deformation first order system of equation, which I'll explain later. And this formulation was implemented in OpenFOAM as an explicit solid dynamic toolkit. However, it was not used for solving FSI problems. So this will be the first application of this formulation for fluid-solid interaction. The advantage of using this formulation is basically it's expressed as a first order conservation laws, similar to what we see in some of the fluid systems. This system is hyperbolic. This will lead us that we can use Riemann solver, which has proven their accuracy in many situations. Next is general notes about the implementation here. I'm using for the code development, I'm using Solids for Form version 2.1, using OpenFOAM version 2012. And for the new solid model, it's derived from the explicit solid dynamic, which is ported to OpenFOAM 2012. So a general explanation about the fluid-solid interaction, but it is usually classified based on the coupling procedure. We have two categories. One is called monolithic, where both of the fluid and solid systems are considered as a single coupled system and solved together. And then we have the partitioned algorithm, where we have each domain solved separately, and then we have a coupling algorithm to communicate between the fluid and solid domain. Solids for Form toolbox incorporate a partitioned algorithm. So I'm just going to show a quick flow chart of what we mean by weak coupling. For the partitioned solver, we have something called weak coupling algorithm. It's basically just start with solving the solid subsystem alone, and then it update the displacement where the solid interface has been moved, and then it moves the fluid mesh. After that, it solves the fluid subsystem, and after that, it takes the forces from the fluid system that is affecting the solid interface and transfer it, and then it continue in the loop. So this is called weak coupled algorithm because it solves each subsystem separately and does not concerned about how it does not concern about the accuracy of what's going on here. But if we want a more accurate approach, we have the strong coupled algorithm. In the strong algorithm, we have an internal loop. Like before we move to the next time step, we have a convergence. Like we check if the both systems have converged completely and reached a mutual solution, a steady solution before we move to the next unsteady time step. So we'll see that more in details later on in the presentation. So also another, I have to explain a little bit about the mathematical background of the Godunov system for people who are not familiar with. So it's basically formulated based on a linear momentum and deformation gradient conservation laws. So here we have both of the conservation laws, as you can see, this one for the linear momentum, and this is for the deformation gradient tensor. These two equations can be combined in one single system of equations, which is usually happens with explicit solvers. And this is the general form of this system where we have U as the conservative variable vector, and F is the flux vector, and S is the source term, in case if there is any source term in the simulation. So we move on to finite volume discretization. I hope everyone is familiar with this, with finite volume discretization, because I'm just gonna briefly talk about it. So we take the differential form and we transform it into integral form. And from there, we take this equation and we discretize it on space, and we get the semi-discrete form where we have now the time where we have now an equation of ordinary differential equation that we can discretize in time also. But this residual is basically the solution of the discretization procedure, where we have now the flux vector here on the right hand side, along with the source term, obviously. This flux vector will be in this algorithm will be evaluated using a Riemann solver, which I'm not gonna explain here. It will take another presentation, but in general, we take the flux vector and we take the normal flux vector actually, and we write it in terms of the traction vector T and the linear momentum P, and we will solve the Riemann solver will solve for this vector and get back the solution for the fluxes, and basically put it back in the equation here. The time derivative in this formulation will be discretized using a single time step, two-stage, second order total variation diminishing Range-Kutta. I know it's the big name, but it's worth it. Because we have a very accurate time discretization, second order, and it's very simple. It's only two-stage, and we solve the system twice, basically, or like in principle, and then we take the average of the fields of the previous two-stage. However, this is still an explicit scheme, and we have to calculate the delta t here, which will be limited due to the CFL number. As I said, the explicit scheme is required a very small time step due to this limitation for stability, and this will require an impractical large number of time steps. So this is also just a quick flow chart of this algorithm, where we start by setting up the system, setting up the domain, and then we start the physical time loop. So here we have a physical time loop, and inside the physical time loop we have the Range-Kut loop. It's very straightforward, where we solve the system twice and then we move to the next time step. I hope the flowchart is visible to everyone. If you cannot see it, please let me know. I can zoom in at any moment and explain further. However, moving to the next thing, so due to this limitation of a very small time step for requirements, we introduced a dual time stepping that will transform the unsteady problem. So it will transform the unsteady problem in physical time step into a pseudo steady problem in fictitious time domain. So what we do is we add a pseudo time derivative. So this is the original equation. And we move this to the right-hand side and we add a fictitious time step, a pseudo time derivative here. So this will help to transform the problem to something we call semi-steady, semi-implicit formulation, in other terms. Because now what we do is we can discretize the physical time step using an implicit second-order backward differencing scheme. So this is now an implicit. However, because we have the pseudo time step, we can now combine everything on the right-hand side. And this is basically the residual, but we call it now L. And we have now this term here, when we just implement the Range-Kut stage again on this new equation. However, this procedure decouples the physical time step from the stability condition. Because what happened is that when we are solving an FSI problem, the fluid domain has its own time step, and solid domain has its own time step. And this might create a conflict when we are solving an explicit solver. In this way, now the physical time step can be only related to the physics of the problem, while the stability requirement for the pseudo time step, delta tau here, we say delta tau, depends on the same requirement, stability requirement earlier with CFL number multiplied here, but we are still decoupled the two time steps separately. So further, just to show you the difference now in the flow chart, we have in the previous single time step, we have a physical time loop and the Range-Kut loop. But if you move to the dual time stepping, now we have an extra loop, which is the pseudo time loop here. So it will check for convergence, obviously, check for convergence here, and then it will move to towards the Range-Kut loop, and then further and the physical time loop again. I will explain this further in the code and how is it implemented. The theory part is done. I will show you now a bit about the explicit solid dynamic toolkit and how is it being implemented. The first part is just the directory, and directory is following the usual open form where we have the application, and we have two solvers here, but we are only considered about the solid form solver. The plastic form solver is not considered in this project, thus it won't be explained. And we have some libraries related to this toolkit. So here, the higher level of the solver, solid form, we have the solid form.c, the source code, along with supporting files that just presented here for organizational purposes and making the code looks nicer. So we have the governing equation solved in here, and we have some boundary condition, update variables, and so on. And of course, the Riemann solver also. So we'll take a look at the higher level solver, solids for form, where the main function has the physical time loop here, which will first, according to the flowchart, will set the time step, the physical time step, because we're still talking about the single time step here. We're not talking about the dual time step. It will store the old time variables, and then it will implement the Range-Kut algorithm, where we solve the governing equation twice, because we're using only two stage. Could be more, depending on your choice. And then we have the update variables after each solution of the governing equations. And then obviously we'll take the average as you saw. So that's for the explicit solid dynamics. I have explained more in the report, so please refer to it if you would like to have more insight. I will talk now about the Solid for Form toolbox and its implementation, main part of it, basically, and the one that we're concerned about. So first, we have the application, again, where Solids for Form is the main solver. And the libraries, it has many libraries, but the most important one is the Solids for Form models that we'll talk about the next slide. And we have the tutorials, for example, fluid-solid interaction, fluids and solids that you can check. So the main libraries, as I said, Solids for Form models it is a, so the best thing about the Solids for Form that is designed in a modular way. So we have the main class, which is the physical model class, and it's an abstract class. So when you say about abstraction, that is the best thing about using OpenFOAM and C++ object-oriented programming. So we have the physics model, and from the physics model, there is a derived class that is fluid models, solid models, and fluid-solid interfaces. So depending on the application that you want, different model will be run. So another look at the solids for form top level or higher level code. The main function will start with creating the physical an object of the physics model using a runtime selection table. So when you see this line open form, you know that there is some runtime selection table going on, and there will be solid model or fluid model or fluid solid interaction model will be selected according to the user. Next is the line is the physical time loop here. So the same similar as before, we have a physical time loop, which is while loop here. And inside the while loop, we'll have physics.set delta t, which is a virtual function. Actually, all the functions that are part of physics class are virtual or pure virtual, because their implementation will be according to the model that we are running. So here we have another important function that we'll see everywhere in the models, which is evolve function. We'll see it more further. So a look at the solid model class that we will be using for developing our new solid model. We see that it inherits the physics model, and obviously it has its own private data, some dictionaries, some fields like point displacement that we will use later on. It has its own member function as we said, the set delta t and evolve. Notice here that evolve is a pure virtual function, which means that the implementation of this function, will be in the derived class. So the derived class that we will look at, or before that, sorry, we have another important function, which is the set traction that we'll also talk about in the coming slides. The derived class, one of the derived class from solid model is the linear geometric total displacement solid class. And it will have its own private data, private function, and of course, the evolve function, which will implement the mathematical model. Similarly, we will follow these guidelines to create our own solid model later on. A quick notice about the fluid solid interface class. It also inherits the physics model. It has its own private data, and just notice, that it also calls or creates a fluid and solid data member from the solid and fluid models. It has its own member function, which is, again, we have evolve, update forces, and move fluid mesh function. So one of the classes one of the coupling models that are available in solid form is the simplest one, called weak coupling interface. And I'm talking about here because it's the simplest one, but you can check other coupling algorithms. So the algorithms start with similar. This is the weak coupling, if you remember from previous slides. So just for comparison, we see that the solution starts by solving the fluid subsystem. It updates the displacement of the fluid-solid interface. It moves the fluid mesh, and then it solves the fluid subsystem. And finally, it forces from the solid system to the fluid system. Sorry, from the fluid system to the solid system. Yeah. For the update forces function that we saw in the previous slide, it calls a very important function which called set traction. So this function will basically take a reference to the interface between the fluid solid interface and the traction at that interface. We'll see more how we will use this function from the solid perspective, because it's a member function of the solid domain, a solid model. Yeah. Now, after we take a big picture of these two solver, we will talk about the implementation of the new solid model in that solid toolbox. This will require so many steps, and honestly, I had to remove so many slides because of time limitation. But please, if you have any question later on, you can reach out, or you can refer to the report, and you can check them. So for a start, let's see that first of all, we create for future perspective for researchers who are interested in creating solid model. I have created this specifically this part. So how to create a base class where you can start from creating a solid model in Solids for Home. So basically what you can choose any solid model. This is just commands of copying and replacing some names and so on. And we call it test model solid. Solid is a prefix for all the derived solid models. So you'll see this solid at the end of every class. This is some more commands to compile and add the libraries to the libraries. Next, we clean up this solid model because we copied from an existing one. So we remove all the libraries that we don't need. We remove all the private member data that we don't need. We remove all the member function also that we don't need. And we keep only the function that are virtual, because they are because you won't be able to compile your code if you don't have the implementation of the virtual function from the derived classes, right? So from there, we move. Similarly, we do the same thing to the source. Previous steps were for the header file. These steps for the source file. Similarly, we remove some file. We keep some file. We remove everything. We keep only the evolve function, for example, because it's a virtual. So next step is now we have to move the explicit solid dynamics implementation to our new classes. So first of all, we will transform the solid model like previous steps to the test model into an explicit Godunov CC solid model. Following the steps, similar steps we repeat here, and the next step is adding the libraries. So all the libraries that are available in explicit solid dynamics in the source file, SRC file directory, we move it to our code. We remove the unnecessary files and folders, and we basically compile. Finally, we include all these libraries in our header file of the class, and we compile and check for errors. The next step is adding member data. So I'm showing only the linear momentum for an example here. So in the header file of the class, we added this way because it's a vector class for the linear momentum. And in the source file in the class constructor, we added similarly. And you can obviously check all other member data in the report or in the combining files, as I mentioned here in the slides. So now we move to the main implementation of the new solid model, where we have to implement the mathematical model in evolve function. So just recall that in the main function, in the higher level of the solids for form, we had this while loop, and it has physics.set delta t, physics.evolve. So this is the evolve function, but this is only calling the function, not implementing the function. So the implementation will come from the explicit solid dynamics toolkit, where we had the Rangikutta and all the pre and post lines, where we have to move to the evolve function now. So the evolve function now in explicit solid in our new solid model is like that. We just simply take all these lines and put it in the evolve function. That's it. You have your solver running now in the solids for form toolbox. However, this will only run the solids problem. It won't solve the fluid-solid interaction because it does not know about the boundary condition, does not know about the coupling algorithm that we are using, and so on and so forth. So for that reason, we have to move on to the we have to move to the final step, which is enabling the explicit Godunov SEC with fluid-solid interaction. And for that, obviously, there are many steps. We'll start with the first one, which is evaluating the required fields that are not available in the previous version of the code, which is explicit solid dynamics. Some of them are like the point displacement, the Cauchy stress tensor, and the increment in the point displacement. So these are required for for making sure that the fields are available for the solver in solids for form to run a FSI problem. The next step is implementing the dual time stepping. So if you remember, in the explicit solid dynamics, there was only the single time step, whereas we need a dual time step for running an FSI problem. So for that, remember that the evolve function we have defined earlier, where the Rangikutta is residing here. And basically, we are at this level. We want to move to the second level by adding the pseudo time loop. So for that, we introduce a do-while correction loop. So this loop will look like this, where we start by do something, which is here the implementation, while not converged. So as long as the solution is not converged, the loop will keep going on, right? So what we need is to move this part inside the do-while loop, as you can see here. Now, if we want to look at the flowchart, we will see that the Rangikutta is at the at the bottom of the flowchart, and then the pseudo time loop or the correction loop is available in the second level. And finally, if we want to see where the physical time step, we know that the evolve function is basically in the higher level solver, where you can see here everything is implemented in the evolve function. Next is interface coupling. So how will the solver know about the fluid-solid interface, right? How will the linear momentum field and how will the traction field will know about this interface? So for this reason, recall the update forces that I told you about. So this function, we said that it calls another function called set traction. So this function update forces is part of the fluid-solid interface algorithm or class. So it will call this on the solid object a set traction function. So this set traction function is defined in the solid model. So now we see that it's part of the solid model class. And what it does, it takes the interface and it takes the traction, phase zone traction here, and call an overlapping function called solid traction. And overloaded function, set traction. And in this function, it takes the solid displacement, solution D here function, return the displacement. Remember, in this solver, they use a solid displacement-based formulation. I might have forgot to mention that, but solid just for affirmation that most of the solid models in solids for form use a displacement-based formulation, where in our case, we are using linear momentum deformation-based formulation. So we have two different fields, which is the linear momentum and traction. So we'll see how we will in the next slide how we will change this and how we will incorporate our fields in this function. So as I said, it's called an overloaded function. So the overloaded function looks like this. It's a bit tricky to understand what's going on here, so I'm just gonna quickly explain, but you can refer to the report again for more details. So what it does, it takes the displacement field, the reference. So just quickly back, I forgot to say something here, that it takes the solution for the displacement field at the boundary. And which boundary? The patch ID, which was received from the fluid solid interface. So there are many levels of a bit complicated, but really nice to understand what's going on in this toolbox. Anyway, so it takes the reference at the boundary, at the interface, along with the traction. So it takes these two fields, or takes these two parameters here. And what it does, it first check the boundary type. So the traction type here, the traction patch at the displacement field, what is the type of this? Boundary? Is it solid traction, finite volume bound vector field or not? If it's if it is solid traction of this type, then what it'll do, it will take the patch ID and reference. It will it's really hard to explain it in words. Sorry for that, but it will recast it. It will cast it into solid traction boundary field, right? So see here. Here we have solid traction, finite volume, and we have traction patch, which will be recast to a solid traction field. And it will take the traction that we had from the fluid forces and assign it through a traction function on the patch ID, which is basically a boundary field class. I hope this makes sense to you. Otherwise, I will just move on and you can ask me later on about it. So what we do now, we have to redefine this function, the set traction function, along with its overloaded function, to include the linear momentum and traction fields. So first, we add the function declarations. We add the function declaration basically to the class header files. So this is the two functions in the header file. The first call and this is the first call and this is the overloaded function. Now we have the first call and we need to modify it. What do we need to do? We have to change this solid solution D into linear momentum and traction field. And what happened here? We also changed the class to explicit Godunov CC solid, right? So now what is it doing? It's calling a reference on the boundary field of linear momentum and traction, because that's what we are solving at the boundary. The second call, similarly, we have to modify it, and we have to call a new boundary condition, a new boundary class, which I call it here explicit solid traction, because we have the same boundary field, but one for the traction and one for the linear momentum. So as you can see here, we have to define two new boundary classes. So the coupling is still not done yet. We have defined the traction condition, but we don't have the boundary condition. And for that reason, we have to define these new classes. However, again, for the time limitation, I could not present how to do this. However, in the next slide, I will explain a little bit what's going on here. So in OpenFOAM, the boundary conditions are categorized as following. So the boundary conditions are part of a library called finite volume patch fields, right? Which is also part of a higher library. But anyway, so finite volume patch fields can be divided in basic, constraint, and derived. So the basic category of the boundary condition includes the fixed value and fixed gradient. And then we have the constraint boundary, which is, for example, the empty when you are using a 2-dimension. So it's constrained boundary condition, which will only reduce the 3D to 2D. And then we have the derived classes, which are basically derived from the basic or constraint, which will be derived from the basic boundary conditions. So like the no slip boundary condition or inlet outlet boundary condition. So as I said, the solid traction boundary condition that we saw earlier before the modification is derived from the basic class based on fixed gradient. So it's a fixed gradient boundary condition. Why? Because the displacement-based formulation that is implemented in solids for form is a Newman type boundary condition. Whereas in our case, when we implemented the new formulation for momentum deformation-based formulation, has a Dirichlet type. And the Dirichlet type basically requires a fixed value boundary condition derived from the basic class. So based on this information, what we will do is we can copy the solid traction boundary condition, change the fixed gradient base to a fixed value, and then we do some implementation to make sure that the boundary condition is implemented correctly in the code. So basically, all these steps are implementation you can find in the report. Finally, this is basically the implementation. I hope it made sense to you, and all these steps and the programming that was behind it and the flowchart. So moving on, I will now talk about the one single FSI benchmark for verifying the implementation and the algorithm, which is perpendicular flap in crossflow. So it's a simple test case 2D where there is an elastic pile here in the middle of the domain, and there is an incompressible fluid coming from the right-hand side, and it's exiting. And we have a wall on the top and wall on the bottom. So basically, this pile is fixed in the bottom side. This is the properties that we are using. So the fluid properties is laminar and incompressible, and the solid properties are linear elastic. So how is this defined in the case directory? What is the case directory structure for solids form in FSI problems? So we have, for example, the case that we're talking about, perpendicular flap, where we have the 0 folder, constant, and system folder. So if we expand these directories, we see that all of them have fluid and solid in almost every folder here. So we have 0 directory fluid, 0 directory solid, constant for fluid, constant for solid, and we have also FSI properties here and physics properties. These are all dictionaries required for the solid model, the FSI model. And in the system also directory, we have a general or overall control directory, along with a fluid directory and solid directory. So we are basically concerned about the solid part here, because the fluid part is it's similar to what you use in pimple form or simple form, right? It's exactly the same. However, for the solid, it will be a bit different. So in the solid part, in the solids for form displacement based, we have the cell center displacement and the point displacement. Whereas in our new formulation, we have to change that. We have the linear momentum in the nodes. So this is LMN, and the linear momentum at the boundary and the traction at the boundary. So these are the fields that we need to define. So at the boundary, what we have in the test case, we have 3 boundaries. We have the interface boundary that is between the fluid and solid, that is basically the wet surface between the fluid and solid. And we have the bottom surface, and we have basically the front and back, which are empty because of the 2D assumption. So remember remember the boundary condition that we have defined earlier in the few slides before, explicit solid traction linear momentum. So here we have to define that here. And it will take no values because the traction that will be coming to this boundary, to this interface, will be coming only from the fluid, right? We don't have any, or for this case, obviously, any force that is being applied to the surface of the solid. The bottom is fixed value. This is a different, also another type of boundary condition that is already defined. I didn't have to do anything about it because it's not related to the FSI implementation. Similarly, we have the traction field where we here again similar boundary condition, but we have here explicit solid traction boundary condition, right? Next, what we have, so now all the fields are defined. We move on to the constant fields. So the first dictionary, we have to define the physics property. So this is the higher level, the first thing that the solver will look at. What is the type of the problem that you're solving? Are you solving a fluid, a solid, or a fluid-solid interaction? Of course, in our case, we are solving fluid-solid interaction problem. Similarly, in the solid part, we have something called solid properties. So in the solid properties, we define what solid model are we using. Here, obviously, we are defining explicit Godunov CC because it's our newly developed solid model. And of course, the solver itself has coefficients such as the number of correctors in the pseudo time step, what is the solution tolerance you want, do you want to implement certain algorithm, do you want to consider incompressibility coefficient, and so on and so forth. Some damping coefficients also is there. So that is the solid part and the FSI part. And in the system folder, I'm just gonna talk about the control dict. So in the main control dict, we define the physical time step. So according to the physics of the problem, we can set whatever value here that we want to solve at. I just want to say that in the fluid part for this test case, I forgot to mention in this slides, we are using implicit solver. So again, this delta t is set accordingly. In the solid part, we also have a control dict, but in this part, we only define the pseudo time step because the physical time step is being taken care by the fluid part, whereas the solid time step is taken care by the solid domain. And of course, we have to define the CFL number here because we're using an explicit solver. So in the finite volume scheme, finite volume solution, there isn't much to explain there. So I'm just going to skip this part because most of the schemes and solution procedure are used in this solver are based on the toolkit itself. So it's similar to OpenFOAM, but it's defined in a different manner. So I'm not gonna dive into this right. Finally, the results. You just run the test case easily. You have all run script, and you'll get your nicely wobbling structure. This is just for verification. And luckily, I got my results aligned with the literature where I compared my solution in this solid form with the results coming from precise software. If people doesn't precise is a kind of a software to compile different softwares together to run an FSI problem, like OpenFOAM, calculus, OpenFOAM with other FEM tools, or even you can use your own tools, your own in-house code. So this will be all for this results. I hope it made sense for you. So as a conclusion, we have developed a new solid model and added to the solids form toolbox. We introduced and developed a dual time step algorithm. And finally, the algorithm was verified against the literature. and which showed good agreement, as you saw. And for the future work, there is lots of scope, honestly, in this work. I just got my hands dirty, as you may say, with the solver, with the toolbox overall, where I can further include material models for nonlinear problems. I can include different Riemann solvers like Rho, HLLC, and HLL, and so on. And what I want to do is the further analysis. So during this project, I didn't have enough time to explore the capabilities of this implementation against against other implementation, other solid models. So this will be also in the future work. And I hope you enjoyed this presentation, and I will thank you all for your patience and